So hi, I'm Aditya. I'm a founding engineer at Finland.ai. And before this, I was a tech lead at Instagram ads and was a software engineer at Google Research before this. So today I'll be talking about data quality in feature engineering and how we leverage great expectations within Finland. So the agenda is basically what exactly is a feature engineering platform for those who do not know. Why is it a hard problem? Then we'll go into the meat of what causes data corruption, and finally, how can we prevent it and how GX is a useful tool for this. So let's start with what exactly is a feature engineering platform. So basically, it's infrastructure to manage the life cycle of features. And this can help you ship features efficiently, reliably, and quickly. So it starts with getting data all the way from the source, such as batch data sources, such as S3, data lakes, delta lakes, or real-time sources like Kafka, Kinesis, doing some transformations on top of it, maintaining some state, and finally providing it for serving at low latency for the models. At the same time, you also want to provide some kind of monitoring on top of it to ensure there is good, healthy data and the data quality is good. At the same time, you want to generate training data for the models. So how do you generate the training data for a given samples? And also you want to promote feature reuse and things around that. So it's basically helping you manage all of the things that are related to features for machine learning. So where do we see it's being used? So it's almost used, we see a multitude of use cases and a lot of companies across the spectrum are using it, right from HR companies to e-commerce companies, media companies. So anytime you see ML in production, you typically have some kind of feature engineering platform. A lot of these companies might not call it feature engineering platform, but they do have something to manage the life cycle of features. A lot of times it's simply like some kind of a data pipeline with Redis on top of it to help you serve it. So this definitely gets the ball rolling, but might not be the most scalable or the right way to do this. So why is this a hard problem? So there are a bunch of issues that can go into it. One is you definitely want to make it very fresh, low latency serving. You want to prevent online offline skews. In terms of authoring, we see that data scientists know how to use Python, but they have to work with an ML engineer who helps put the model in production. There's a data engineer who helps with the data pipelines. You want testing CI/CD like it's done in software for ML. There's a lot of DevOps, but primarily, which is the topic of this talk, is how do you also ensure good data quality and drift monitoring in terms of feature engineering? So let's go into that. And so what are the different causes of data corruption? So as you can see, there are a bunch of places where engineers can shoot themselves in the foot when they deal with ML. And a very common story that we hear is, oh, we tried to put ML in production, we worked on it for a few months, but it did not work out. Like the metrics are just not moving. And as you can see, there are just so many ways, and it's important to understand how are the different ways people can make these mistakes and what are the things you need to keep in mind to prevent these. So I'll be going into a few of these things and how to prevent this, but definitely there are a lot other ways where it can go wrong. So the first is changes or failures to upstream pipelines. This is sort of an obvious one where features rely on a web of data pipelines. And at the time of authoring, these might make sense. But let's say someday later, the owner of a data source upstream decides that for his use case, it's not seconds, but milliseconds that makes more sense. Suddenly, all the features downstream are 1000x, and things don't make sense. And it might just be too late to capture these failures. On the other hand, these pipelines might just fail, and you might be serving stale data. This is an interesting one, which is time travel. So to understand this case, imagine you're a bank and you're trying to create like a fraud detection model. So as part of this, you obviously need to generate a large amount of training data for millions of transactions. But when you generate the training data, what you need to keep in mind is each of the data that's used for the event happens before when it happened. To explain more, let's say you have a million transactions and there's a specific transaction that happened a week ago. So you should only use the data that happened prior to the event and not after it. Else you'll be leaking the data from the future into the past. And this itself could just destroy the model performance. For example, you have a feature which is the number of fraud transactions the user has seen. If you take all the transactions up to now and not up to when the event happened, you literally told the model that, hey, there was a fraud. So obviously, it's not going to work. Then there is online offline skew. Uh, Typically, we see that training data is a large amount of data and is often generated using some kind of SQL pipelines. But online services require low latency, so they use the technology of the app like Python or JavaScript, and there is some massaging of the feature values at the end, and they use some key value store. So clearly, there is some difference in the feature definitions, and this can cause skew. Apart from that, another source is the training data is a large amount of data, but when you generate it, it's extremely fresh because you just generated it. But the online features could depend on the batch data getting uploaded every day. And this can cause staleness issues because during the morning, the data was fresh, the features were fresh. But as the day progressed, they got more stale. And hence, this can introduce like a lot of online offline skew. The next is feature drift. This is also like an obvious one is that as time progresses, the features keep drifting, and this could be due to several factors, simply due to things like seasonality, weather, or unforeseen events like an economic downturn. And the model performance keeps dropping with time. So it's a very gradual decay in performance, which needs to be controlled by, let's say, model retraining. This is also like another interesting source of issues. So this is like feedback of the model. So in this case, imagine you're trying to create an ML model, which is trying to generate the news feed for the end user. And the model realizes that, oh, like people generally prefer cats more to dogs because there are a little bit more cats. So it generates a news feed which contains a lot more cat stories. And because there are a lot more cat stories, you see that a lot of people are clicking on these cat stories, and hence the feature values for the cats are more. And the models are like, oh, this is great. I should show even more cats. And hence the what started as a 51-49 split of cats and dogs would end up being 75-25. And hence there's a large difference between the distribution of the data in the training time as well as the inference time. So these kinds of feedback loops can also cause data corruption. So how do you defend against such kind of a data corruption issue? So there's a large things that you can do. These are just some of the things that you can think about. One is monitoring the feature distribution. This is, I believe, like the underlying thing that you need to take care of. Because at the end, what is model training? It's basically trying to learn the distribution of the training data and hoping that at inference time, the distribution is similar to that of the training time. So here you could do things like measure the statistics of the training data and having calculating the statistics of the online or inference data, ensuring they are not too off. You could also measure the statistics of the inference data day after day or week after week and ensure that they don't skew a lot. Uh, the other thing you could do is logging the features. Now, this is a very simple one, but actually helps prevent a lot of the online offline skews. It obviously prevents time travel because what you're doing is you're not generating training data. You're just logging the features at inference time and only using that for training data. Now, this sounds simple, and but it's actually used in a lot of places, especially at big companies like Facebook or Google. For example, when I was at Instagram ads, this is all we could do because you cannot afford to generate training data for billions of users across thousands of features. That's way too compute intensive. So the way putting features in Facebook would look like is you take a week to put it into the feature framework. It was called F3, Facebook feature framework, and then wait for another week for the data to roll in. Then you would look at the quality of the data and you're like, oh, there's a bug. And then you would modify the feature and then you would fix it. And then you wait for another 2 weeks to collect the training data. And then finally you would be able to train. So this obviously fixes the correctness issues, but you can see that the speed of iteration gets really slow. And then this ends up in you leaving Facebook and trying to start a feature engineering platform company. But yeah, that's one way that people typically go after removing these kinds of data corruption. The next one is not suppressing the errors. So as you saw that features depend on like a web of data pipelines. But sometimes people try and catch and handle these errors, which causes these things to silently fail. So it's important to fail fast and ensure that things get brought up so that the engineers can handle it quickly. Uh, the next one is retraining models. This is an obvious one is to help deal with the feature drift, which happens with time. This will just retrain at a regular cadence, which is defined by your business problem. The extreme end version of this is online training, in which a model is constantly getting trained by the new data that's constantly coming in. So this is definitely used at large companies like Facebook or Google, but this only makes sense if you are making like small incremental improvements in the model gives you millions of dollars. Else the cost of maintaining an online trained model far outweighs the incremental benefits that you would get. So it's a tricky one, but just most of the time, just retraining the models would take you far ahead. The last one over here is making resources immutable. So let's go back to the story when you had a feature which depended on a web of data pipelines, uh, and the user just changed it from, let's say, seconds to milliseconds. Now, when you made this change, if you don't allow this change because the feature downstream gets affected and that is immutable. So you would get an error that hey, that feature is immutable, so you cannot change it. So he should instead go and upgrade the versions for all of the things that depend on this data set. So this ensures that everything is being done consciously and not silently. Also, if most of the things make sense, he could just increment the version. But if he is not sure, he could then contact the owner of that feature set and ask that, hey, I'm making this change. Can you fix this too? So making things immutable and not allowing things to fail silently is a large part of it, I would say, and also like helping you monitor the feature distribution. So these are some of the things. Now let's look at how do you use GX for some of these use cases. So as I mentioned, like monitoring is a large part of dealing with these issues. So GX obviously has like you can do automated validation. It has like a large set of expectations that it has, and if something that doesn't support, you can obviously add your own. And as data comes in, you could keep profiling it, so it has some kind of an automated data validation. It obviously helps with better error handling since you can be proactive about what is happening in the system by catching errors maybe right at the source itself rather than waiting it to corrupt all of the data downstream. It does definitely facilitates data documentation because now you can better understand the data by just looking at the code. For example, if you have something called an age feature, but you also have an expectation on top of it, which says typically between 18 to 30, 90% of the times you automatically understand that, oh, this is talking about young people. Now, you cannot call the feature young age because older people could also use it. So you definitely don't want to restrict it, but you by just reading the code, you get a better sense of what's happening behind the scenes. It also helps with test-driven development uh, because when you write the expectations, it's like writing your test first and then writing your code. So you write your expectations first and then let the data keep rolling in. And that makes you more conscious about what is the kind of data that you're expecting to look at, which automatically also translates to data profiling, is you can get a much better sense of what is happening behind the scenes as the data rolls in. For example, you initially defined age to be between 18 to 25, 90% or 95% of the time. And now slowly, as the data is coming in and you look at the expectations, you see that, oh, there are a lot of 50-year-olds and above, which is now occupying 20% of my roles. So probably like there are more older people that are using your product. So now you should think about features which could help generalize to these people. Hence, you constantly have a fresh view of what is happening behind the scenes, and it helps with data profiling. Finally, it definitely helps increase, and this is the most important of all, is it increases the trust in your results. Like the most common story is, as I mentioned, like the team is sitting together, is trying to put ML in production. Things are not working, and they just have no idea why it's not working. It's because in when you put ML in prod, there are just so many things that could go wrong that no one has clue. And by using a tool like Great Expectations, you could just rule away a bunch of these cases by knowing that, oh, these feature values were definitely not null, so it's probably doing fine, or the values were between these things. So hence that part of the system is ruled out. So it just increases the trust in different parts of the thing. And that's just like the test-driven development. Like the more tests you have, the more confidence you gain. And GX just aligns well with the philosophy about that. Uh, so one thing which is interesting, which a lot of people might know, is obviously the Great Explorations is great for batch data. It does a phenomenal job. It has got integrations like Spark, etc. But it's just not for batch, but also can be used for streaming data. So in case of streaming data, what you could do is you could just window it to a granularity that suits you. Let's pick hourly durations. You could buffer the data for the hour and then do mini batch based processing. So now essentially you would have all of your expectations for every hour of the day. So now when you want to look at the expectations across the day, all you got to do is aggregate 24 data points. And now you have an idea of, oh, what happened across the day. A week is just an aggregation of over 150 data points. So now using just mini batching and calculating expectations, you can do validation across any kind of time range window. So now you could also look back in time, and let's say you were seeing some issues and you suspect it was something that happened last night. So you could just pick the window that started at midnight and went up to 7 a.m., aggregate those 7 data points and get a better sense that, oh, the feature values were actually pretty null during night. So let me go upstream and look at the expectations during the same window for the upstream data sources. And hence, you can very easily handle stream data too by using GX, which obviously is great for batch data. So now let's look at code example of how Fennel uses layered expectations for its own use case. So this is an example of a data set, which you can just think about it as a table, and it has the columns which is described above. So here you have passenger, gender, age. We also define like the great expectation syntax is pretty similar to what is defined in the documentation. Or if you write your expectations and you refer to which column are you talking about. So we obviously support both single column as well as multi-column expectations. And this is something that's really cool is that now you can look at columns across the row itself and make stronger guarantees about your data. One thing which we definitely distinguish is between type restrictions and our data expectation. For example, if you have age, you would want it to be between 0 to 100. So if a data point of 200 is coming in, you don't want it to enter the system at all because that can corrupt the data. No one is 200 years old. But if it's someone is 98 years old, it's probably okay. And you do want to let them into the system, but you also want to ensure that they are not more than 5% of the users. So you do want to set some expectations and also some type restrictions to ensure that data does not get corrupt. But at the same time, you are having a very good sense of what's going on behind the scenes. And when you finally like write these expectations, you can then have a better sense of what's happening. So here you have defined a time range of like what happened in the past 1 hour. What are the expectations that you defined? What are their definitions? How many of them failed, succeeded? You can now change the time range window. You could go from an hour to 2 hours or a week and understand it how things are working across the week. You can click on the errors and look at what were the data points that were failing your expectations and get a better sense of what are the things that are changing in the underlying system. You could also overlay it with something that happened a week ago or a day ago to get a better sense of the delta and see is there any drift that's happening in your expectation. So yeah, that's basically how we use Great Expectations. So you could definitely learn more about us at docs.finland.ai. And if you like the slides, you could go to go.finland.ai/data quality.
All right, Ditya. Thank you. Wow, that was that was very, very information packed. I like how you just casually drop the slide in on how you do batch processing too, and or how you work with streaming data. It's something we actually also get a lot of questions on, and the approach you're taking is also pretty similar to kind of what we're thinking, and yeah, let's talk more about that. Like I think we can also I love to learn more about how you use that, and yeah, maybe we can like kind of create a blog post together around some of that.
Yeah, that makes a lot of sense. Yeah, would love to collaborate on it.
Yeah, that's great. Let's open it up for questions, and then while I think everyone's maybe you can go back to the slide you have showing the code. I can you talk I see you have a expectations decorator there.
Yeah.
Can you and can you tell us a bit more about how that works and why did you choose that approach?
Sure. So the way it looks in our thing is we define a bunch of data sets and you have pipelines between these data sets, which say how do you get data from one data set to another. And at the rate expectations is just describing that, hey, this function is going to contain my list of expectations. So it's just a decorator which is indicating to the system that take all of the things that are returned by this function and generate all of the expectations that is contained within it. So we have a very decorator-centric approach. Like everything is marked by decorators to indicate what each things are doing. So this is just a decorator which marks that this is a list of great expectations that you can, where we will apply on the data set that it contains them. It's like a member function and it directly corresponds to its columns.
Gotcha. Okay. Makes sense. Thanks. And then I think we had a hand raised from Ning Hao. Ning Hao, do you have a question?
Yeah, I guess can you guys hear me okay?
Yeah, we
Yep.
can hear you.
Cool. Yeah, I guess the question, and also though, this particular, by the way, really nice talk. I guess detail though, that got me really interested is that about the data quality on the feature engineering platform. So I assume you actually have a feature store, which obviously stores the data that after the feature engineering. That's just basically that we have raw data, which is more like human readable, but after feature engineering, it becomes a human not readable, but the ML understand for it, right? I guess do you, I see that in your example, so you're actually running GX against the raw data. Have it ever occurred to you to run the GX against the feature engineered data that's stored in the feature store?
That's a great question. So yeah, this example is just showing it against the raw data. But the way it works is, as you can see, it's a decorator at the rate expectations, and you can attach this in any function defined anywhere. So here it's a data set. We also have something called a feature set. So you could attach this inside the feature set, which is a pretty downstream data set in some sense. And you could attach these expectations. So let's say you aggregate data on top of this and you build a feature on top, and then you just define at the rate expectations inside that feature set, and you can calculate expectations for that. So yeah, this is so the way it's modular and hence it's pluggable at any point in our system. So we do that. Yeah.
Cool. Yeah, I guess obviously though, using GX measure quality against the human readable data, it's common because that's what the expectation is, right? But when you against the feature engineered data, though, typically humans makes no sense of what that is. Though I was just that's kind of like a revolutionary the idea of like I was thinking about, but would be nice to see some of the examples. So I'll probably follow you guys on Slack and hopefully we can chat more on that front. But that's more about the feature store rather than GX, but it's a really cool, I guess, use case there. Yeah.
Sure. Makes sense, yeah. But at the end, like features also like a normal feature is what's the number of clicks the person has in the past 7 days. So it's like a count-based feature and it's defined as a column in our feature set. And now you can define like an expectation on that number of clicks in the past 7 days and ensure it has some data properties. They're more than happy to follow up and answer.
Yeah, sounds good. Cool. Yeah, that's from me. Back to you, I guess, Josh. Right.
Yeah. Yeah. Thanks, Inghao. Yeah. I would love to follow this conversation too. I would, yeah, see if we can put it in. Maybe you can ask it in the data quality discussions channel that we have, and then I would love to follow along. I imagine, and then yeah, if you start there, let me see if I can tag a few folks who might know other examples of how community members in the past or our users have apply expectations against non-human readable data. I wouldn't be surprised if, I mean, with the way everything is LLMs these days, I wonder if there are people even applying this stuff to like vector embeddings and things. So yeah, love to see what some of these use cases are. Yeah, I haven't thought about that. That's good. Yeah, I'd be really interested too. Cool. Thanks for the question, Kyle. Anyone else have any questions? Let me open up chat as well. While we're waiting, another one that occurred to me was I think data lineage is something that also comes up a lot. Aditya, have you thought about data lineage, how this overlaps? Yeah, well,
so
what's
lineage is
kind of thinking
pretty
there?
central. Yeah, lineage is pretty central to us. So like when I mentioned about the slide of pipelines. So that's essentially like this data flows into another data. So as I mentioned, like for us, each of them is a data set, and then you define a pipeline between it. And in our console, we show an entire graph of this data pipe into this data pipe into that data. So we follow the entire lineage, and we also have immutability constraints as you cannot simply modify a data set without letting the other ones who depend on it also know. So everything is extremely, you need to tell the system that by incrementing the version and nothing happens silently and fails behind the scenes. So we do track the data lineage as well as, in our case, features could depend on features too. So we do track feature lineage too, and also the lineage between how the feature depends on the data set. So everything is like a graph, and we have visualizations for it in our system, which allows you to quickly scan through and understand what's going on.
Cool. And is Fennel opinionated about how you build your data pipelines? Like what frameworks, tools, or all that?
Yeah, I would say we are a pretty opinionated platform. Currently, what we believe is that all data scientists know to write pandas and love to write pandas, and hence we have tried to keep the ramp up pretty low. So your pipelines are essentially pandas code which you write, but it scales for the streaming and batch use cases very easily. So yeah, I could like go to my docs, and that has like a bunch of use cases. Uh, so you have like these data sets and pipelines. So this is how you would get data from one data set to another data set by writing a pipeline. And this is pure like pandas code that you would write. And then you could do group bys, filters, aggregations, all those kinds of things which pandas allows you to do using these pipelines. And then we generate like a lineage of all of the data sets and the feature sets that are in our pipeline. Does that answer your question?
Yeah, I'm sorry. What? I couldn't catch the what kind of code that you're.
Well, this is like pandas code. Like yeah, you just like
Pandas code. Okay, sure.
pandas,
Yeah.
pandas. So
Okay,
everything
got it.
is like a pandas data frame, and almost everyone out there knows to write pandas. Yeah.
Right. Yep. Makes sense.
Yep.
Any other questions? All right, everybody. Then in that case, let's pause it there. Any questions you have? Let's take it to the take it to the Slack channel. Aditya, thank you so much for this. Like, I feel like I personally learned a lot about feature engineering and a very interesting way to apply new ways to apply good expectations to data. So yeah, so thanks a lot.
Thanks for the
Yeah,
opportunity.
yeah, thanks for the great talk. Like Bruno said, and thank you everybody for coming. So have a wonderful week, everybody. Have a wonderful month. Hope to see you all next month.
Thanks, Josh.
Yep, the recording will be up soon. Thank you. Bye.
Yeah.